Before we begin, a quick note. The information in this presentation is for educational and informational purposes only, based on our in-depth research and analysis of industry practices. When making strategic technology decisions for your organization, always conduct your own thorough due diligence. Imagine a single line of code, buried deep inside a private repository at Apple, that orchestrates the secure boot-up sequence for 1 billion iPhones. Or a tiny algorithm at Netflix that saves the company $100 million a year in streaming costs. These pieces of code, these digital crown jewels, don't just live on some developer's laptop. They exist inside a fortress. A digital fortress so secure, so efficient, and so powerful that over 90% of Fortune 100 companies have built their entire innovation engine inside of it. That fortress is GitHub Enterprise. And today we are getting the keys. Now you might be thinking, I know GitHub. I use it every day. I push code, I make pull requests. What's the big deal? And that, right there, is the most expensive misconception in modern software development. Using the free, public version of GitHub and thinking you understand GitHub Enterprise is like driving a go-kart and thinking you know what it feels like to pilot a Formula One car. They both have 4 wheels and a steering wheel, but they are fundamentally different machines, built for entirely different purposes. The public version is for collaboration. The enterprise version is for domination. This isn't just about private repositories or a few extra admin features. It's about a complete philosophical shift in how the world's most successful American tech companies build, secure, and ship software at a scale that would break any other system. They're not just using it to store code, they're using it as a strategic weapon. And for the next few minutes, we are going to pull back the curtain and show you exactly how they do it. We're going to deconstruct the 3 core pillars that separate the hobbyists from the hyperscalers: ironclad security, hyperspeed collaboration, and automated governance. By the end of this video, you won't just know what GitHub Enterprise is. You'll understand the secret architecture of innovation that powers Silicon Valley and beyond. Let's start with the pillar that keeps CEOs and chief technology officers awake at night: ironclad security. We've all heard the horror stories. A junior developer working late on a Friday accidentally commits an AWS secret key to a public repository. Before he can even realize his mistake, automated bots crawling the internet have found it, spun up 1,000 crypto mining servers in his company's cloud account, and racked up a 7-figure bill. The company makes headlines for all the wrong reasons. Trust is shattered, and careers are ruined. This isn't a hypothetical. It happens every single week. This is the kind of existential threat that companies like Microsoft, Ford, and Coca-Cola simply cannot afford. So what do? They build their fortress on a foundation called GitHub Advanced Security. This isn't just a feature. It's an entire integrated security platform that acts like an immune system for your entire code base. And it starts with something called secret scanning. Think of secret scanning as a team of digital bloodhounds that are constantly, relentlessly sniffing every single line of code that anyone, anywhere in your organization, tries to commit. Before that git push command even completes, it's been scanned. It's looking for the specific patterns of over 200 different types of tokens. Amazon Web Services keys, Google Cloud credentials, Azure Storage keys, Twilio tokens, Stripe API keys. The moment it finds a match, it doesn't just send a polite email. It blocks the push. It stops the breach before it can ever happen. It instantly alerts the security team and the developer with the exact location of the exposed secret. For a massive organization with tens of thousands of developers, this isn't a nice-to-have. It's the digital equivalent of having armed guards at every door and window of your corporate headquarters, 24/7. It completely changes the game from reactive damage control to proactive prevention. But what about vulnerabilities already buried deep within your existing code? The subtle bugs, the potential exploits that an attacker could use to steal customer data or take down your service. This is where the second weapon in the advanced security arsenal comes in: code scanning. Powered by the most sophisticated code analysis engine on the planet, CodeQL. To understand why CodeQL is such a revolutionary leap, you have to understand how traditional security tools work. Most of them are like grammar checkers. They look for simple patterns, known bad practices, and common mistakes. It's useful but limited. CodeQL is different. It doesn't just read your code, it understands it. It treats your entire codebase as a queryable database. This is a profound idea. It means your security team can ask incredibly complex questions of your code, like, show me every single place in our entire multi-million line codebase where user-provided input flows into a database query without being properly sanitized first. That's the kind of question that could uncover a critical SQL injection vulnerability. Finding that with a traditional tool would take a team of expensive penetration testers weeks, if they found it at all. With CodeQL, you can write a query once, and then run it automatically on every single pull request, across every repository in your entire organization forever. It's like having a world-class security researcher personally review every single line of code before it ever gets merged into your main branch. It finds vulnerabilities that other tools miss, and it finds them at the earliest possible moment, while the developer is still working on the feature. It doesn't just tell them, there's a problem here. It shows them the exact data flow, from the source of the tainted data to the sink where the vulnerability occurs, making it incredibly easy to understand and fix. When you combine secret scanning with code scanning, you create a powerful security feedback loop. You're not just catching mistakes, you're educating your developers in real time. You're building a culture of security from the ground up. This is how elite American tech companies sleep at night. They're not just hoping they're secure, they are systematically engineering security into the very fabric of their development process. They've turned their source code repository from a potential liability into their single greatest security asset. And we've only just scratched the surface of the first pillar. But a fortress is useless if the people inside can't get any work done. Secure code that never ships is just an expensive academic exercise. This brings us to the second and arguably the most transformative pillar: radically accelerating development velocity through seamless, at-scale collaboration. To understand the revolution, you first have to understand the old way of doing things. Picture a global tech giant in the early 2000s. They have 10,000 engineers spread across a dozen campuses, from Silicon Valley to Bangalore. They're all working on one massive, monolithic product. How do they coordinate? The answer is, painfully. It was a world of endless email chains with 200 people CC'd. A world of weekly sync-up meetings that lasted 3 hours and accomplished nothing. A world where Team A couldn't do their work because they were waiting on Team B, who was in turn blocked by Team C in a different time zone. Progress was measured in quarters, not days. A simple bug fix could get lost in a bureaucratic maze for months. The friction wasn't in writing the code. The friction was in everything around the code. It was in the communication, the handoffs, the approvals. It was a system designed for a different era, and it was grinding innovation to a halt. Now, contrast that with how a company like Netflix or Microsoft operates today using GitHub Enterprise. They've transformed their entire development process by building it around a single central hub. It's not just a place to store code anymore. It has become the central nervous system of the entire engineering organization. It's the digital headquarters, the town square, and the assembly line all rolled into one. And the heart of this entire system is a deceptively simple concept: the pull request. To a non-developer, a pull request or PR sounds like a dry technical process. But in reality, it is the single most powerful collaboration tool ever invented for software development. It is a living, breathing document that tells the complete story of a change. Let's walk through it. Imagine a developer at a major e-commerce company needs to add a new one-click buy button to their mobile app. First, she writes the code on her local machine. When she's ready, she opens a pull request on GitHub. This is where the magic begins. This isn't just an email saying, "Hey, can you look at my code?" The pull request automatically kicks off a whole symphony of events. First, a suite of automated tests runs. Does the new button break the shopping cart? Does it slow down the page load time? Thousands of checks run in minutes, providing an instant quality gate. If any test fails, the PR is blocked. No human time wasted. Simultaneously, the security scans we talked about in the last part are running. Is this new code introducing a vulnerability? Is it using a library with a known exploit? Again, an automated check. The security team doesn't have to be a bottleneck. They've encoded their rules directly into the workflow. Once the machines give their blessing, the humans step in. The developer tags 2 of her teammates for a code review. Now, this review doesn't happen in a meeting room or over a laggy screen share. It happens right there inside the pull request. Her teammates can leave comments on specific lines of code. One might say, "This variable name is a bit confusing, can we change it?" Another might suggest, "There's a more efficient way to write this function that will use less battery on the user's phone." It becomes a rich, asynchronous conversation. The original developer can respond, make changes, and push updates. The entire history of the debate, the suggestions, the decisions, the reasons why, is preserved forever attached to the code itself. A new engineer joining the team 6 months from now can look at that pull request and understand not just what was changed but why it was changed. The institutional knowledge is captured automatically. Once her teammates approve, maybe a project manager gets a final look. They see the green check marks from the automated tests, the security scans, and the human reviewers. With one click, they approve. And that final click can trigger the last step, automatically deploying the new button to millions of users. From a line of code on a developer's laptop to a live feature on your phone, all orchestrated through one central, transparent, and auditable workflow. This pull request model solves the problem of coordinating a small team. But how do you coordinate 1,000 teams? This is where American tech giants are using GitHub Enterprise to pioneer a concept called inner sourcing. Inner sourcing is exactly what it sounds like, applying the principles of open-source software development inside the walls of a private company. In the open-source world, if you're using a project and you find a bug or need a new feature, you don't just file a ticket and hope the maintainer gets to it. You can fix it yourself and submit your changes back to the project. It's a culture of contribution, not just consumption. Companies like Google and IBM realized they could foster this same culture internally. Their code bases were becoming so massive that no single person could understand it all. Teams were becoming siloed, reinventing the wheel because they didn't know another team had already built a component that did exactly what they needed. With inner sourcing on GitHub Enterprise, that all changes. Let's say the photos team at a big tech company needs a new, high-performance video compression algorithm. They discover that the company's video streaming team built a world-class one for their own product 6 months ago. In the old world, the photos team would file a request. It would go into a backlog, get prioritized in the next quarter, and maybe if they were lucky, they'd get the feature in 9 months. In the inner sourcing world, a developer from the photos team can go directly to the streaming team's repository, which is visible to them inside the company's GitHub Enterprise instance. They can read the code, understand how it works, and then fork it to create their own copy. They can make the modifications they need, and then open a pull request back to the original streaming team's project. Now, the experts on the streaming team are a part of the conversation. They can review the changes, suggest improvements, and ensure the new code meets their high standards. The photos team gets their feature in a matter of days, not months. The streaming team gets an improved component contributed by another team for free. And the entire company benefits because the core, shared component is now more robust and serves more use cases. This breaks down the silos. It turns the entire company's engineering talent into one massive fluid pool of resources. It creates a marketplace of ideas, where the best code wins, regardless of which team's budget it came from. It completely flattens the organization and eliminates the "not my department" problem. The friction of inter-team dependency, one of the single biggest drags on velocity in large companies, simply evaporates. You are no longer blocked by another team's priorities. You are empowered to improve any piece of the company's software yourself. This is a profound cultural shift. It moves companies from a need-to-know basis to a need-to-share culture. Suddenly, every line of code, every feature discussion, every architectural debate is searchable and discoverable by anyone in the engineering org. This transparency builds trust and fosters a culture of collective ownership. It's not their code or my code. It's our code. By combining the atomic, workflow-centric power of the pull request with the macro, organization-busting power of inner sourcing, American tech companies are achieving a state of development flow that was unimaginable a decade ago. They are shipping better software, faster, with fewer bugs, all because they've turned their code platform into a collaboration platform. They've solved the human scaling problem. But what if you could take this entire supercharged workflow and put it on autopilot? What if the very act of writing code could trigger a cascade of automated quality checks, security audits, and even deployments to millions of users, all without a human ever touching a button? That's where the third pillar comes in. Building an elite automation engine that turns your repository into a self-driving factory for software. This factory isn't built of steel and concrete. It's built of code. And the assembly line is powered by a system called GitHub Actions. Now, if you've only used the free version of GitHub, you might think of Actions as a neat little tool for running some tests. But inside these tech giants, it's the central nervous system of their entire engineering organization. It's the engine that never sleeps. So what is it, really? At its core, GitHub Actions is an event-driven automation platform. That's a fancy way of saying, when something happens in your repository, automatically do something else. That something happening could be anything. A developer pushing new code, another developer opening a pull request for review, or even something as simple as a new issue being filed. The do something else part? That's where the magic begins. Imagine a junior developer, let's call her Sarah. On her first day at a company like Salesforce, she's given a small bug to fix. She finds the problem, writes a few lines of code, and pushes her changes up to GitHub. The second her code arrives, the factory whirs to life. An automated workflow. A series of steps defined in a simple text file right alongside the project's code, kicks off. The first robot on this assembly line is the style inspector. It's a process called linting. It scans Sarah's code not for what it does, but for how it looks. Is she using tabs instead of spaces? Did she forget a semicolon? These might seem like trivial things, but with thousands of engineers, maintaining a single consistent style is critical for readability and preventing simple mistakes. If her code fails the style check, she gets an instant automated report. No senior engineer had to waste 10 minutes pointing out a formatting error. The machine did it. Sarah fixes the style issue and pushes again. The style inspector gives a green check mark. Now the code moves to the next station, the testing gauntlet. This isn't just one test. It's hundreds, maybe thousands of tiny automated tests that verify every piece of the software still works as expected. Does logging in still work? Does the search bar still function? Can a user still update their profile? These are called unit tests and integration tests, and they form a safety net that catches regressions before they ever reach a real user. If Sarah's change, no matter how small, accidentally broke something completely unrelated, this station will scream bloody murder. The build fails, she's notified immediately, and a potential disaster is averted. But American tech companies don't just build software for one type of computer. Their customers use Windows, macOS, Linux. They use different versions of programming languages, different browsers. How do you ensure your code works flawlessly on every possible combination? Manually testing this would take weeks. The automated factory does it in minutes using a feature called a build matrix. The workflow file essentially says, take this code and run the entire testing gauntlet, but do it simultaneously on a virtual machine running the latest version of Windows. At the same time, do it on a machine running macOS. And do it on 3 different versions of Linux. And while you're at it, test it against 3 different versions of our core database. The matrix explodes one testing job into dozens of parallel jobs, all running at once in the cloud. Within minutes, you have a comprehensive report card showing exactly where your software works and where it doesn't. This isn't just quality assurance. It's a massive competitive advantage. It's the confidence to ship code knowing it's been battle tested against a dozen different environments without a human lifting a finger. Once the code passes this gauntlet, it moves to the next station, the assembler. This is where the code is actually compiled and packaged. It's turned from human-readable text into a machine-executable program, a Docker container, or a mobile app package. This artifact, this final product of the assembly line, is then stored, ready for deployment. Now, here's where GitHub Enterprise really separates the pros from the amateurs. The free version of GitHub lets you use runners, the virtual machines that execute these jobs, that are hosted by GitHub. They're great, but they're a shared public resource. A company like Apple or Amazon cannot, and will not, run their top-secret source code on a shared public machine. It's a massive security risk. Instead, they use a feature called self-hosted runners. They build their own private, secure fleet of thousands of runner machines inside their own data centers or private cloud. They have complete control. Need a supercomputer with 8 high-end GPUs to train an AI model as part of your workflow? You can build a self-hosted runner for that. Need a machine with a specific proprietary security chip to sign your code? You can build a self-hosted runner for that. This gives them limitless power and total security. Their code, their build process, their secrets. It all stays within their own fortified walls. But it gets even more sophisticated. With tens of thousands of developers, how do you prevent chaos? How do you ensure every single team is following the company's mandated security protocols? You can't just send an email and hope for the best. GitHub Enterprise allows them to create what are called reusable workflows and organizational policies. The central security team can define a master workflow, a golden path, for what it means to safely build and test software at the company. This workflow might include steps like scan all code for known security vulnerabilities, scan all third-party libraries for outdated packages, and check for any hard-coded secrets like passwords or API keys. Then, the organization can set a policy that says, no code can be merged into our main branch on any repository, unless it has successfully passed this mandatory security workflow. It's no longer a choice. It's a non-negotiable toll booth on the highway to production. This is how you enforce excellence at scale. It's not about trusting 50,000 developers to do the right thing every time. It's about building a system where it's impossible for them to do the wrong thing. This entire automation engine has one ultimate goal: to increase developer velocity, to take all of the repetitive, manual, error-prone tasks off the plates of their most expensive and valuable employees. The goal is for a developer to be able to merge their code and immediately move on to the next problem, confident that the factory will handle the rest. The factory will test it, secure it, package it, and get it ready for release. It transforms the development process from a series of manual gates and checks into a fluid, automated river that flows directly from a developer's mind to the customer. So now we have this incredible self-driving factory. It's secure, it's powerful, and it's churning out perfectly built software at an incredible pace. But this entire system is built on one fragile assumption: that the code going into the factory is safe. What happens if a developer, in a moment of haste, accidentally commits a file containing the master key to their entire customer database? The world's most efficient automation factory just became the world's most efficient data breach machine. How do you scan every single line of code for secrets before it even enters the assembly line? That's the next layer of the fortress. This fortress layer is built on a simple, yet revolutionary, idea in the security world called shifting left. Imagine your entire software development process is a timeline, an assembly line. On the far right, you have the finished product running live, used by millions of customers. Traditionally, that's where most security happened. You'd hire teams to try and break into the live application, find the cracks, and then send a frantic report back to the developers on the far left of the timeline to fix it. It's slow, it's expensive, and it's like inspecting a car for safety after it's already been sold and is driving on the highway. Shifting left means moving all of that security intelligence, all of that inspection, as far to the beginning of the assembly line as possible. You check the car's brakes while it's still just a blueprint. You test the engine before it's even bolted to the frame. In the world of code, the furthest left you can go is the developer's own computer, at the exact moment they try to add their work to the factory line. This is where GitHub Enterprise unleashes one of its most powerful tools: GitHub Advanced Security, or GHAS, as it's known internally. And the first line of defense in GHAS is called secret scanning. The problem it solves is one of the most common and most devastating security failures in modern tech: the hard-coded secret. An API key to a payment processor, a password to a production database, an access token for a cloud provider like Amazon Web Services. These are the digital keys to the kingdom. And developers, under pressure to ship features fast, often make a simple human mistake. They'll temporarily paste a key into the code to test something, fully intending to remove it later. But then they get distracted. A meeting runs long, a new urgent bug comes in, and they forget. They commit the code, key and all, and push it up to the central repository. In a public GitHub repository, that's a catastrophe. Automated bots are constantly scraping public code for exactly these kinds of keys. A leaked AWS key can be found and used to spin up thousands of dollars in crypto mining servers in less than a minute. But even in a private enterprise repository, it's a ticking time bomb. That key is now a permanent part of the project's history. Anyone with access to the code, hundreds, sometimes thousands of engineers, contractors, and potentially one day an attacker who gains internal access can now see that key. So, how does GitHub's secret scanning solve this? It's a two-pronged attack. First, for every line of code that already exists in the company's repositories, GitHub is constantly scanning. It's not a human reading the code. It's a highly sophisticated pattern matching engine. GitHub has partnered with over 100 of the biggest service providers on the planet: Amazon, Google, Microsoft Azure, Stripe, Twilio, you name it. These companies provide GitHub with the unique patterns of their secret keys. An AWS access key, for example, always starts with AKIA, followed by 16 uppercase letters and numbers. A Stripe API key has a prefix like sk_live_. GitHub Scanner races through petabytes of code, looking for strings that match these highly specific formats. When it finds one, it doesn't just flag it. In many cases, it automatically notifies the provider. So if an AWS key is found, GitHub can ping Amazon, who can then automatically revoke the key and notify the owner, neutralizing the threat almost instantly. This is the safety net, catching secrets that have already been spilled. But the real magic, the true shift left innovation, is a feature called push protection. This is the bouncer at the front door of your codebase. When a developer on their laptop writes code containing what looks like a secret and tries to push it to the central GitHub repository, the push is rejected. It's blocked. Right there in their terminal, a message appears saying, "Hold on. It looks like you're trying to commit a potential secret. Here's the file, here's the line number, and here's the type of key we think it is." This push has been blocked. This is a profound change in workflow. The developer gets instant feedback. There's no waiting for a security team to run a weekly scan and send them a nasty email. The mistake is caught and corrected in seconds, before the toxic code ever touches the shared factory floor. It turns security from a punishment into a helpful, immediate guardrail. It's like a smart spell checker, but for catastrophic security leaks. And this is where the enterprise part becomes critical. A startup might be able to get by with the default patterns, but a Fortune 500 company has its own secrets. Internal database connection strings, proprietary API keys for internal services, special encryption tokens. They have their own unique formats that only exist inside their walls. GitHub Enterprise allows these companies to define their own custom patterns. The security team can go in and, using a language of pattern matching called regular expressions, teach the scanner what their internal secrets look like. If you see a string that starts with prod_db_ and is followed by 32 alphanumeric characters, that's a key to our customer database. Block it immediately. Now the fortress is customized. The bouncer isn't just looking for common, public-style keys. It's trained to recognize the company's own crown jewels. This level of customization is essential for massive organizations like Ford or Johnson & Johnson, whose internal systems are just as critical as their cloud infrastructure. The scale of this operation is mind-boggling. At a company like Microsoft, which owns GitHub, you have over 100,000 developers. They make millions of code commits every single month. The idea of a human security team reviewing that fire hose of code for accidental secrets is a fantasy. It's not just impractical, it's mathematically impossible. You can't hire enough people. You can't review fast enough. Automation is the only answer. And this system provides a single pane of glass for the people in charge. The Chief Information Security Officer doesn't have to guess about their exposure. They can log into a security overview dashboard and see every single secret alert across the entire organization. They can see trends. Are more secrets being leaked this quarter than last? Which teams or repositories are the most frequent offenders? This allows them to target training and resources effectively. It transforms security from a game of whack-a-mole into a data-driven science. Think about the impact. A single engineer working late on a Friday makes a tiny copy-paste error. In the old world, that error could sit dormant for months, a hidden vulnerability, until it's discovered by an attacker, leading to a front-page data breach, costing the company hundreds of millions of dollars in fines, lost revenue, and reputational damage. In the new world with GitHub Enterprise, that engineers get push command fails within 2 seconds. An automated message points out the exact error. The engineer says, "Oh right," removes the key, puts it in a proper secrets manager where it belongs, and successfully pushes the clean code. The multi-million-dollar breach never happened. It was prevented before it was even born by an algorithm in the span of a coffee sip. That is the power of a truly integrated, developer-focused security platform. You've secured the keys to the kingdom. You've built tripwires and automated guards around the most common and dangerous human errors. The fortress is stronger. But what about the code itself? A locked door is great, but it doesn't help if the wall next to it is made of paper. What if the code, even without any leaked secrets, contains fundamental flaws, vulnerabilities that a clever attacker could exploit to create their own way in? How do you check the structural integrity of every single brick being laid in your digital fortress? The answer lies in treating code not as text but as data. It's about building an automated system that can X-ray every single brick, looking for hairline fractures and structural weaknesses the human eye would miss. This is the world of static application security testing, or SAST, and it has become the bedrock of secure development inside America's tech giants. But the old way of doing this was clunky, slow, and frankly kind of dumb. Early SAST tools were little more than glorified search functions. They'd look for specific, problematic patterns in the code, like finding the word password next to a hard-coded string. It was useful, but it generated a massive amount of noise, false positives that would drive developers crazy. It was like a security guard who flags every single person wearing a black coat as a potential burglar. Soon, everyone just starts ignoring the alarms. This is where GitHub's acquisition of a company called Semel in 2019 completely changed the game. Semel was the creator of a revolutionary technology called CodeQL. And to understand why CodeQL is so powerful, you have to stop thinking about code as a static file of instructions. You have to start thinking of it like a living, breathing system, a network of roads where data flows like traffic. CodeQL doesn't just read the code, it models it. It builds a complete, queryable database of your entire code base, understanding the relationships between every variable, every function, every call. It's the difference between looking at a map of a city and having a live, real-time GPS model of every car, every turn, and every destination. Imagine a master detective investigating a potential crime scene before the crime has even been committed. A regular security tool is like a beat cop. It walks the perimeter, checks for broken windows, jiggles the doorknobs. It's looking for obvious, known signs of trouble. It's useful but limited. CodeQL, on the other hand, is the Sherlock Holmes of code analysis. It doesn't just look at the scene. It reconstructs the entire sequence of events. It understands the flow. It knows where a potential intruder, in this case malicious data, might enter the building. It knows every hallway they could travel down, every door they could pass through, and every critical asset they could potentially reach. It's not looking for a broken window. It's identifying a path from the open front door, through the lobby, up the service elevator, and directly into the CEO's office. Let's make this real with one of the most common and devastating vulnerabilities in history: SQL injection. This is where an attacker can trick a web application into running malicious database commands by entering them into a simple input field, like a search bar. The old-school scanner might try to find this by flagging any code that builds a database query using text concatenation. This is noisy because sometimes it's perfectly safe. The developer gets 1,000 warnings, 99% of which are false alarms, and the real threat gets lost in the static. CodeQL's approach is fundamentally different. It performs what's called taint tracking. It sees a piece of data that originates from an untrusted source, like a user input field on a website. It taints this data, marking it as potentially dangerous. Then, it follows that specific piece of tainted data on its journey through the entire application. It watches it get passed from function to function, variable to variable. It's tracking the suspect, and it keeps tracking it until one of two things happens. Either the data is passed through a sanitizer, a function specifically designed to clean and validate user input, rendering it safe. In that case, CodeQL knows the threat has been neutralized. Or it watches as that raw, unsanitized, tainted data flows all the way to a sink, a sensitive function, like the one that executes a database query. And at that exact moment, the alarm bells ring. But it's not just a generic alarm. GitHub Advanced Security, powered by CodeQL, integrates this directly into the developer's workflow, the pull request. The moment a developer tries to merge code containing this flaw, an automated check fails. And the feedback it gives is incredibly precise. It doesn't just say, "You have a potential SQL injection on line 487. It says, "The data originating from the username field on line 32, which is an untrusted user input, flows through these 5 functions, remains unsanitized, and is then used to construct a database query on line 487. This is a critical vulnerability. Here is the exact path the data took. Here is a suggestion on how to fix it. And here is a link to an article explaining precisely why this is so dangerous." This changes everything. It transforms security from a roadblock into a guardrail. For decades, security was a separate team that would run a scan a week before a major launch, dump a 200-page PDF report on the developers' desks, and bring the entire process to a screeching halt. It created an adversarial relationship. Developers saw security as the department of no. But with CodeQL integrated into GitHub Enterprise, security becomes part of the creative process. It's immediate contextual feedback. The developer who just wrote the code, who has the entire logic fresh in their mind, can fix the issue in minutes, not weeks. They also learn as they go, making them better, more secure coders over time. This is the embodiment of the shift-left philosophy that has taken over Silicon Valley. You're moving security from the far right end of the development timeline to the absolute earliest possible point, the moment the code is written. And for the business, the return on investment is staggering. The cost to fix a security vulnerability is not linear. A bug caught by the developer as they write it might cost a few dollars of their time. That same bug, if it's found in testing, can cost 10 times that. If it makes it into production, it can cost 100 times more. And if that bug is exploited by an attacker, leading to a massive data breach, well, the cost can be billions. The 2017 Equifax breach, caused by a single unpatched vulnerability in a web application framework, has cost that company over $1.4 billion to date. When you look at it that way, the licensing fee for GitHub Advanced Security isn't an expense. It's one of the cheapest insurance policies a technology company can buy. This isn't just a static tool either. The power of CodeQL is that it's a living language. GitHub's own world-class security research team, along with a global community of experts, are constantly writing new queries to find new types of vulnerabilities. When a massive zero-day threat like the Log4 shell vulnerability shocked the world in late 2021, it was an all-hands-on-deck emergency for every company on the planet. Within hours, GitHub's team had written and published a CodeQL query that could instantly identify it. Any company using GitHub Enterprise could, with a few clicks, scan their entire software portfolio, millions upon millions of lines of code, and know their exact exposure. It was a global immune response deployed at the speed of software. So, the fortress walls are now being built with structurally sound bricks. The blueprints are being checked in real time for architectural flaws. The secrets are locked away in a digital vault. The fortress seems secure. But what if the danger isn't in how you build the fortress, but in what you build it with? Modern software isn't built from scratch. It's assembled. It's built on a foundation of hundreds, sometimes thousands of third-party open-source components. What happens when one of those foundational bricks, sourced from an outside supplier, is already compromised? What happens when the enemy isn't trying to break down your door, but is already inside the shipment of materials you just had delivered? This is the nightmare scenario that keeps chief information security officers awake at night. It's called a software supply chain attack. And in 2020, this theoretical nightmare became a catastrophic reality for the United States in an incident so audacious, so sophisticated, it's now spoken of in the same hushed tones as a digital Pearl Harbor. The company at the center of the storm was a Texas-based firm called SolarWinds. Now, if you're not deep in the IT world, you've probably never heard of them. But inside the networks of the world's most powerful organizations, their software was everywhere. SolarWinds makes a product called Orion, a powerful platform used by IT administrators to monitor and manage their computer networks. It's the digital dashboard, the central nervous system for thousands of businesses and government agencies. To do its job, Orion needs incredibly deep, privileged access to a company's entire network. It's trusted implicitly. It was one of those foundational bricks used to build the digital fortresses of the Fortune 500, the Pentagon, the Department of Homeland Security, the Treasury Department, you name it. They were a trusted supplier. And that trust is exactly what was weaponized. Sometime in late 2019, hackers believed to be from Russia's Foreign Intelligence Service, the SVR, breached SolarWinds' own internal network. But they didn't steal data or deploy ransomware. They did something far more patient, far more insidious. They studied how SolarWinds built and compiled their software. And then, with surgical precision, they injected a tiny malicious fragment of code, just a few hundred lines, into the Orion source code. This malicious code was a dormant backdoor. It did nothing at first. It was designed to pass all the automated checks. Then, when SolarWinds went through its normal legitimate process of building a software update, this poison pill was baked right in. The update was tested, approved, and then, crucially, it was digitally signed by SolarWinds' own legitimate security certificate. This was the masterstroke. A digital signature is a stamp of authenticity. It tells a customer's computer, this software is genuine, it comes from the real SolarWinds, and it has not been tampered with. In March of 2020, SolarWinds pushed this poisoned update out to its customers, and over 18,000 organizations, including the highest levels of the United States government, dutifully downloaded and installed it. They were letting the Trojan horse right through the main gate, because it was disguised as one of their own trusted soldiers. Once installed, the malicious code lay dormant for 2 weeks, and then it quietly called home to a command and control server controlled by the hackers. From there, the attackers could pick and choose their targets. They moved silently through the networks of America's most sensitive institutions for over 9 months, completely undetected, stealing emails, accessing secrets, and establishing a foothold that we are still trying to fully understand and eradicate to this day. The SolarWinds attack fundamentally changed the conversation around cybersecurity. The old model of building a strong perimeter, A high wall around your castle was proven obsolete. The attackers didn't need to break down the wall. They had themselves delivered inside the supply shipment. For every American tech company, the question became terrifyingly urgent. How do we trust the code we rely on but didn't write ourselves? How do we inspect every single brick that comes into our construction site? This is where GitHub Enterprise shifts from being a development platform to a critical defense system for the software supply chain. The first step in defending against this threat is visibility. You cannot protect what you cannot see. And in a modern application, what you see in your own repository is just the tip of the iceberg. Your code depends on dozens, sometimes hundreds of open source packages. And each of those packages depends on other packages which depend on still others, creating a massive, complex, and often invisible web of dependencies. GitHub Enterprise tackles this head-on with a feature called the dependency graph. It's automatically generated for every repository. Think of it as a complete, comprehensive family tree for your software. It crawls through your project's manifest and lock files and maps out every single library, every single piece of third-party code your project is built on, no matter how many layers deep. Suddenly, the invisible becomes visible. You have a complete inventory of every single brick being used in your project. This alone is a huge leap forward. You now have a map of your potential attack surface. But a map is only useful if you know where the dangers are. That's where the next layer of defense comes in, Dependabot. If the dependency graph is the map, Dependabot is your automated 24/7 security patrol. It constantly scans your entire dependency tree and cross-references every single package against a massive, continuously updated database of known security vulnerabilities. The moment a vulnerability is disclosed in a package you're using, even a package that one of your dependencies depends on for levels down, Dependabot knows. And here's the game-changing part. It doesn't just send you an email alert that adds to your notification fatigue. In many cases, Dependabot will automatically create a pull request in your repository. A pull request that bumps the vulnerable package to the next secure version, complete with release notes and a compatibility score. It doesn't just tell you the door is unlocked. It walks over and locks it for you. All the developer has to do is review the change, run their tests, and click Merge. This transforms security from a burdensome manual chore into a streamlined, semi-automated part of the daily workflow. It lowers the friction for being secure so much that it becomes easier to fix vulnerabilities than to ignore them. But what about the unknown threats? Dependabot is fantastic for known vulnerabilities, the ones that have been discovered and documented. The SolarWinds hack, however, was a zero-day vulnerability. It was a novel attack, a brand new piece of malicious code that no existing scanner was looking for. How do you defend against an enemy you don't know exists? This is where GitHub Advanced Security, a core component of the enterprise offering, brings in its most powerful weapon, code scanning, powered by an engine called CodeQL. CodeQL is revolutionary. It doesn't just match patterns of code like a traditional scanner. Instead, it treats your code like data. It analyzes your entire codebase and builds a queryable database from it. Then, you can run queries against this database to find potential vulnerabilities. Think of it like this. A traditional scanner is like a security guard with a list of photos of known criminals. They can only catch people who are on that list. CodeQL is like giving that guard the ability to ask questions like, show me anyone who is loitering near a sensitive area without proper authorization, or show me any instance where a key was left unattended. It allows you to search for the patterns and variants of vulnerabilities, not just specific known examples. You can find whole classes of bugs. For a large enterprise, this is transformative. They can use the thousands of queries written by GitHub's world-class security research team, but they can also write their own custom CodeQL queries. Do they have a specific internal cryptography library that must be used in a certain way? They can write a query to find any developer who uses it incorrectly. Are they worried about a specific type of injection attack that is unique to their architecture? They can write a query to hunt it down across every single one of their thousands of repositories. This tool allows a company to codify its security expertise and then apply it automatically, at scale, across the entire organization, stopping vulnerabilities before they are ever checked in. It's the shift from reactive defense to proactive threat hunting, embedded directly into the developer's workflow. The fortress isn't just checking the bricks at the gate anymore. It's performing a deep, structural analysis on every single one before it's even allowed near the construction site. And this proactive defense mechanism has evolved to hunt for a far more insidious threat, one that isn't a bug or a flaw, but a key, a literal key. think about the most critical assets a developer works with every single day. It's not just the logic they write, it's the credentials they use. API keys for third-party services, database connection strings, private certificates, OAuth tokens, the keys to the entire digital kingdom. For decades, the cardinal sin of software development has been hard-coding these secrets directly into the source code. It's the equivalent of taping your house key to your front door with a note that says, "Please don't use." And yet, under the pressure of deadlines, it happens. A developer is testing something locally, they hard-code a key to get it working, and then, in the rush to commit, they forget to remove it. In the past, this was a ticking time bomb. The secret would sit there, buried in the code history. Maybe a code review would catch it. Maybe a specialized, after-the-fact scanning tool would find it days or weeks later. But in the worst-case scenario, if that code was ever made public, or if an attacker gained access to the repository, the game was over. We've seen companies suffer catastrophic breaches, racking up hundreds of thousands of dollars in fraudulent cloud computing bills in a matter of hours, all because a single developer accidentally committed a single AWS access key. The damage isn't just financial, it's a deep, reputational wound. This is where GitHub Enterprise transforms from a code host into a digital vault guardian. It's called secret scanning, and it's not just a feature. It's an emergency response system built directly into the git push command. The moment a developer tries to commit code that contains a recognizable secret, GitHub can block it. But it gets so much deeper than that. GitHub has partnered with an ever-growing list of service providers. We're talking Amazon Web Services, Microsoft Azure, Google Cloud, Slack, Stripe, Twilio, you name it. When the scanner detects a pattern that looks like, say, an AWS key, it doesn't just flag it. It securely communicates with AWS, using that provider partnership, and asks, "Is this a valid active key?" If the answer is yes, a multi-stage alarm is triggered. The provider, AWS in this case, is immediately notified and can automatically revoke the key, rendering it useless to any potential attacker. The developer is alerted. The organization's security team is alerted. The commit can be blocked before it ever even pollutes the main branch. This isn't just finding a needle in a haystack. It's vaporizing the needle mid-air before it can prick anyone. The speed is the critical factor. We're talking about a response time measured in seconds, not days or weeks. This shrinks the window of opportunity for an attacker from a gaping garage door to the width of a human hair. And for American tech giants, this isn't just about public cloud keys. GitHub Enterprise allows them to define their own custom secret patterns. Imagine a massive financial institution. They have their own internal authentication tokens, their own proprietary database connection formats. They can teach GitHub's secret scanner exactly what those patterns look like. Now their own internal bespoke keys to the kingdom are protected with the exact same automated, high-speed vigilance as a common Google Cloud credential. It's a custom-tailored security blanket for their entire software development lifecycle. So now we've secured the code itself with advanced security, and we've secured the secrets embedded within that code. The fortress walls are strong. The keys to the gates are protected. What's the next vector of attack? It's the Trojan horse. It's the code you didn't write. Every modern application is built on the shoulders of giants. It's a complex tapestry woven from hundreds, if not thousands, of open-source packages and dependencies. Your developers might write 50,000 lines of code, but the final application could be running millions of lines of code when you include all the libraries for handling web requests, database interactions, data processing, and everything in between. This is the software supply chain, and securing it has become one of the single greatest challenges in modern cybersecurity. We all remember the fire drill that was Log4j, a vulnerability discovered in a single ubiquitous logging library, used by millions of Java applications worldwide, sent shockwaves through the entire tech industry. Companies scrambled for weeks, trying to answer one terrifyingly simple question. Are we using this? And if so, where? It was a global panic, a desperate hunt through mountains of code to find one specific, vulnerable dependency. GitHub Enterprise tackles this head-on with a suite of tools designed to give companies a godlike view of their software supply chain. The most prominent of these is Dependabot. On the surface, it's simple. Dependabot automatically scans your project's dependencies, checks them against a massive, constantly updated database of known vulnerabilities, and if it finds a problem, it automatically opens a pull request to update the package to a safe version. But in an enterprise context, it's so much more. This isn't just about version bumps. Dependabot provides a rich tapestry of information. It doesn't just say, "This version is vulnerable." It says, "This version is vulnerable. Here is the exact nature of the vulnerability. Here is its severity score. And here is a pull request to the next secure version with a calculated compatibility score, telling you how likely this update is to break your build." It gives developers not just a problem, but a solution with a clear risk assessment. This creates a culture of proactive, continuous security patching. Instead of a massive, painful fire drill once a year when a Log4j-style vulnerability hits the news, security becomes a steady, manageable drumbeat of small, incremental updates. The security team can then use GitHub's central dashboard to see the dependency health of the entire organization at a glance. They can see which teams are quick to patch and which might need a nudge. They can enforce policies that say, no code can be deployed to production if it has a known critical vulnerability in its dependencies. This culminates in one of the most important artifacts in modern software development, the Software Bill of Materials, or SBOM. An SBOM is exactly what it sounds like: a complete inventory, a detailed ingredients list of every single component that makes up a piece of software. Following major supply chain attacks, the US government has even started mandating that any software sold to federal agencies must be accompanied by an SBOM. For large companies, generating and maintaining these SBOMs used to be a monumental, manual, and error-prone task. With GitHub Enterprise, it's practically a side effect of doing good work. Because GitHub already knows all your code, all your dependencies, and the entire history of how they were built, it can generate a comprehensive SBOM for any project on demand. This turns a massive compliance headache into a simple API call. It provides a level of transparency that is becoming the new standard for enterprise software. When a customer, a regulator, or an internal auditor asks, "What is in this software?" you don't have to launch a month-long investigation. You just hand them the list. By tackling code vulnerabilities, embedded secrets, and the entire software supply chain, these companies aren't just building applications. They're building digital fortresses on audited, inventoried, and constantly reinforced foundations. They've secured the what, the code, the keys, the components. But the real magic, the thing that ties it all together, is securing the how, the process, the intricate dance of automation that takes a developer's idea and forges it into a production-ready reality. And that's where the true power of the ecosystem begins to shine. This automation, this CI/CD pipeline, is no longer just a convenience. It's the central nervous system of modern software development. And for a CISO at a Fortune 500 company, that means one thing: it's the single biggest attack surface they have. Think about it. We spend millions on firewalls, on endpoint detection, on securing the code at rest. But the pipeline? The pipeline is code in motion. It's a trusted process that takes source code from inside the castle walls, transforms it, and then ships it out to the world. If an attacker can poison that process, they don't need to breach the walls. They can just wait for the delivery truck to arrive at their door, carrying a Trojan horse they themselves helped build. This is the nightmare scenario that keeps security professionals up at night. Not a direct assault on the source code, which is heavily audited, but a subtle manipulation of the build process itself. Imagine a developer uses a popular, open-source tool in their GitHub Actions workflow to, say, compress images. It's been used millions of times, it's trusted. But one day, the maintainer's account is compromised, and a new version is published. This new version does everything the old one did, but with one tiny addition. It scans for any environment variables that look like API keys or cloud credentials, and silently sends them to a remote server. The source code of the application never changed. The pull request looks perfect. Every code scan passes. But the moment it hits the build server, the company's most sensitive secrets are exfiltrated. Game over. This isn't theoretical. It's why securing the pipeline has become an obsession for enterprise tech. And GitHub Enterprise provides the granular controls to do it. The first layer of defense is the build environment itself, the GitHub Actions runner. By default, your jobs run on runners hosted by GitHub. They're clean, they're fast, they're convenient. But for a large enterprise, they're a black box. You don't control the network they're on. You don't control the underlying operating system image. So, the first move for any security-conscious company is to switch to self-hosted runners. These are virtual machines that the company provisions and controls, running inside their own cloud environment, on their own virtual private network. This is a monumental shift in security posture. Now, that runner can be firewalled off from the public internet. It can be configured to only access specific internal resources, like an internal artifact repository or a database of secrets. You control the machine image so you can pre-install all your security scanning tools, your custom certificates, and ensure it meets your corporate compliance standards. But they go a step further. Static, long-lived build servers are a liability. If one is compromised, an attacker could lurk there for weeks, observing builds, stealing code. The modern approach is ephemeral runners. A new pristine virtual machine is spun up from a golden image for every single workflow job. It does its one task, compile the code, run the tests, and then it's destroyed, completely vaporized. Any malware, any foothold an attacker might have gained is wiped out with it. The next job gets a brand new, sterile environment. This practice dramatically reduces the window of opportunity for an attacker. It's like building a new clean operating room for every single surgery. Okay, so the environment is locked down. But what about the workflow code itself? That malicious action we talked about? This is where enterprises get ruthless about their supply chain. They don't allow developers to just pull the latest version of any random action from the GitHub marketplace. Instead, they enforce policies. Rule 1. You must pin your actions to a specific, immutable commit hash, not a floating tag like latest. This ensures that the code you audited is the exact code that will run forever. It prevents the rug from being pulled out from under you. Rule 2. For the truly paranoid, you don't use the public action at all. You fork it. You create an internal copy of that action within your own GitHub organization. Your security team vets it line by line. From that point on, your developers can only use the internally approved version. You've effectively air-gapped your CI/CD process from the public marketplace, creating your own private, trusted ecosystem of automation tools. Now we get to the secret sauce, the credentials. The old way was to store secrets, cloud keys, API tokens, as encrypted variables in GitHub. It works, but it means you have long-lived, powerful credentials sitting around. The new and vastly more secure method is to go passwordless. This is accomplished using a technology called OpenID Connect, or OIDC. It sounds complex, but the concept is brilliant. Instead of giving your workflow a permanent key to your cloud provider, the GitHub Actions runner can request a temporary, short-lived token directly from Amazon Web Services, Google Cloud, or Azure. It proves its identity, that it is a specific workflow from a specific repository, triggered by a specific event, and the cloud provider issues a token that is only valid for a few minutes and has only the precise permissions needed to do its job, like permission to upload this one file to this one storage bucket. When the job is done, the token expires and is useless. There are no long-lived keys to steal. An entire class of attack vectors is just gone. With a hardened ephemeral runner, vetted internal actions, and passwordless OIDC authentication, you've built a formidable fortress around your build process. But how do you enforce this across thousands of repositories and tens of thousands of developers? You can't just send a memo. This is where GitHub Enterprise's policy as code features become the crown jewel. Using repository rule sets and organization-wide policies, a central administrator can define the non-negotiable laws of software development for the entire company. They can create a rule that says, to merge code into a production branch, you must have 2 senior developer approvals. The branch must pass all unit tests, and it must have passed a CodeQL static analysis scan, a dependency scan, and a secret scan. Furthermore, these scans must have been run on one of our approved, self-hosted, ephemeral runners. This rule isn't a suggestion in a wiki. It's a hard gate. The merge button in the pull request will literally be grayed out, unclickable, until every single one of those conditions is met. It makes the secure path the only path. This is the real meaning of shifting left. It's not just about finding bugs earlier. It's about programmatically enforcing security and compliance at the earliest possible moment, the moment of creation, and making it impossible to build software any other way. What you're creating isn't just a software artifact anymore. You're creating a verifiable audit trail. You have a cryptographically signed attestation that proves which developer wrote the code, who approved it, the exact commit hash of the source, the exact hash of the build script that ran, the logs from the security scans it passed, and the identity of the hardened ephemeral machine it was built on. This entire chain of evidence, this digital provenance, is the foundation of a secure software supply chain. It transforms the final product from a mysterious black box into a transparent, verifiable asset. We've built the perfect artifact, forged in a secure, automated factory, and we have the signed paperwork to prove it. But what good is a perfectly forged, secure artifact if it gets stolen or tampered with the moment it leaves the factory floor? Securing the storage and deployment of that artifact, that's the final critical mile. This final mile is where the most spectacular failures happen. It's the digital equivalent of building the world's most secure vault, only to have the combination written on a sticky note left on the door. You've built your code, you've tested it, you've scanned it for vulnerabilities, you've even created a cryptographically signed tamper-proof artifact. Now what do you do with it? Where do you put this digital crown jewel? For years the answer was, well, kind of a mess. Companies would spin up their own artifact repositories like Artifactory or Nexus, which were powerful but added another complex system to manage, secure, and pay for. Or worse, they'd push their container images to public registries like Docker Hub. Now Docker Hub is fantastic for open source projects, but for a multi-billion-dollar enterprise, using a public registry for private, mission-critical software is like storing your company's trade secrets in a public library locker. You can put a lock on it, but you're still in a public space with public-facing APIs and a massive attack surface you don't control. A single misconfigured permission, a single leaked credential, and your core intellectual property, the very engine of your business, is exposed for anyone to download. This is the problem GitHub set out to solve with GitHub Packages. It's not just a feature, it's a fundamental shift in thinking. Instead of your source code living in one place and the compiled results of that code living somewhere else entirely, GitHub Packages says, let's keep them together. It's a private, secure, versioned registry for all your software artifacts, living right alongside the code that created them. Think about that. When you look at a container image in the GitHub Container Registry, you don't just see the image tag. You see a direct, unbreakable link back to the exact commit, the exact pull request, the exact workflow run that produced it. The entire history, the entire chain of custody is right there. There's no more detective work trying to figure out which version of the code is actually running in production. It's all connected. And it's not just for Docker containers. We're talking NPM packages for your JavaScript front-ends, Maven and Gradle packages for your Java backends, NuGet for your .NET services. It becomes the single source of truth for every component that makes up your application. This co-location of code and artifact is a security game changer. Your permissions are unified. The same teams and access rules that govern your source code now govern the binaries built from it. If a developer leaves the company, deactivating their GitHub account instantly revokes their access to not just the source code, but also to every package they ever had permission to publish or read. You cut off access at the root, and the entire system is secured. So now our perfectly signed artifact is stored in a secure, private, auditable vault. The next question is, how do you get it out of the vault and into the hands of your customers? How do you deploy it? This is where the guardrails become absolutely critical. What stops a single developer from pushing a catastrophic bug to millions of users at 3 a.m. on a Tuesday? What prevents an experimental feature from accidentally being shipped? The answer lies in one of the most powerful and, frankly, underappreciated features of GitHub Enterprise: environments. An environment is simply a name for a target where you deploy your code. The classic examples are development, staging, and production. But you can create any you want. QA, performance testing, beta users. The magic isn't in the names. It's in the protection rules you can apply to them. Let's focus on the most important one: production. This is the holy of holies. This is your customer-facing application. You cannot afford mistakes here. So, inside GitHub Actions, you define your production environment and you start adding rules. The first and most important rule is required reviewers. This is the human circuit breaker. By enabling this, you can specify that before any code can be deployed to production, a specific person or a specific team must manually approve it. Imagine this scenario. A workflow is triggered to deploy a new update. The code has passed all the automated tests, all the security scans, everything looks good. The GitHub action dutifully builds the artifact, signs it, and is ready to push it to your servers. But because it's targeting the production environment, it stops. Just pauses. And a notification goes out to the on-call engineering team, or maybe the director of engineering. Someone with authority has to go into GitHub, look at the deployment request, see exactly what's about to change, and click a big green approve button. Without that manual human sign-off, nothing happens. The deployment is held in limbo. This single feature prevents a whole class of disasters. It stops the accidental deployment. It stops the rogue developer. It forces a moment of deliberate consideration before a change impacts real users. At major tech companies, this isn't a suggestion. It's a mandate. The security team might require that a member of their team approve any deployment that touches authentication code. The database team might require approval for any deployment that includes a database migration. You can build a sophisticated, multi-layered approval process that mirrors your company's organizational chart and risk tolerance. But it gets even better. Another protection rule you can add is a wait timer. Let's say a deployment to production is approved. Instead of it happening instantly, you can configure a delay, say 30 minutes. Why? It's a cooling off period. It gives the team a final window to catch a last-minute issue or to realize, wait, we forgot to notify the marketing team about this launch. It also allows for strategic timing. You can approve a deployment during business hours, but set a timer so the actual release happens at 2 a.m. when user traffic is at its lowest, minimizing potential disruption. Then you have deployment branches. You can lock down an environment so that it can only be deployed from a specific branch like main. This simple rule enforces discipline. It means no developer can deploy their half-finished feature branch directly to production, bypassing the entire pull request and code review process. All code must first be merged into the stable, protected main branch before it's even eligible for a production deployment. Let's put it all together and see what this looks like for a top-tier engineering organization. A developer finishes a new feature. They open a pull request from their feature branch into the main branch. This automatically triggers a GitHub Actions workflow. It runs the unit tests, the integration tests, the static analysis, the vulnerability scans. The developer's teammates review the code and approve the pull request. It gets merged into main. The moment it merges, a second workflow is triggered, the deployment pipeline. This workflow checks out the main branch, builds the Docker container, signs it with SigStore, and pushes the signed artifact to the private GitHub container registry. Now the workflow attempts to deploy this new version to the staging environment. The staging environment has no protection rules, so the deployment happens automatically. The new code is now running on internal servers that mirror production. Automated end-to-end tests run against staging to make sure the whole application works together. The quality assurance team does manual testing. Everything looks great. Now someone triggers the final step. Promote to production. The same workflow run now targets the production environment. And here the brakes slam on. The workflow pauses. It needs approval. The lead site reliability engineer gets a notification on their phone. They review the changes, check the staging environment's health metrics, and see that everything is stable. They click approve. The 30-minute wait timer begins. 30 minutes later, with no alarms raised, GitHub Actions securely authenticates with the cloud provider using OpenID Connect, so there are no long-lived secrets stored in GitHub, and deploys the new container. The entire process from pull request to production is fully automated, yet punctuated by critical human-in-the-loop checkpoints. Every single step is logged, auditable, and tied directly back to the source code. This isn't just a CI/CD pipeline. This is a secure software factory, with a fortified vault and an armored convoy for delivery. This is how modern elite tech companies operate. They combine the velocity of automation with the wisdom of human oversight. They've built a system that allows them to move fast without breaking things. They've solved the final mile. But deploying the code is not the end of the story. In fact, it's just the beginning. Because the moment your code hits production, it encounters the one thing you can never fully replicate in any test environment: reality. And reality is messy. It's unpredictable. It's a million users all clicking the same button at once because a celebrity tweeted a link to your site. It's a network hiccup in a data center halfway across the world that causes a cascade of failures you never anticipated. It's a subtle memory leak that only manifests after running for 72 hours under a specific, bizarre load pattern. For decades, the mantra in software was shift left. Find bugs earlier. Test more. Catch problems before they ever see the light of day. And that's still critically important. But the most elite engineering organizations in America have realized that's only half the battle. They are now aggressively shifting right. Shifting right isn't about being sloppy and letting bugs slip into production. It's the exact opposite. It's about instrumenting, observing, and learning from the most complex, most valuable test environment in the world, the real one. It's about embracing the chaos of production and building systems that can not only withstand it, but can also learn from it. And in this high-stakes world of live systems and real-time user impact, GitHub Enterprise has become the command and control center. When a monitor screams that latency has spiked, or the error rate for a critical service just shot past its threshold, what happens next is a race against time. The old way was a frantic scramble. Pagers go off. Engineers jump into a conference call. desperately trying to figure out what changed. Was there a deployment? Who deployed it? Where are the logs? It was organized panic. The new way is automated, streamlined, and centered entirely within GitHub. An alert from a tool like Datadog or New Relic doesn't just send a message to a Slack channel. It uses an API to instantly open a new high-priority issue in the relevant GitHub repository. This issue is automatically populated with the critical data: the service that's failing, the specific error, a snapshot of the metrics, and a link back to the observability dashboard. It automatically tags the on-call engineers. In a single second, the entire context of the problem is captured and delivered to the right people in the place they already work. This GitHub issue is now the incident's war room. It's the single source of truth. Every discussion, every query that's run, every hypothesis that's tested is documented as a comment. But here's where the real magic happens. Because this issue lives in GitHub, it's not isolated from the code. With a click, an engineer can see the last 10 commits that were deployed to that service. They can see the exact pull request that introduced the change. The discussion, the code review, the test results, it's all there. The gap between what's breaking and what changed collapses from hours of detective work to mere seconds of navigation. This is about dramatically reducing one of the most important metrics in the industry: mean time to recovery, or MTTR. The faster you can fix something, the less impact it has on customers and the business. And American tech giants are using GitHub Actions to turn recovery into a one-command operation. If a bad deployment is identified as the cause, an engineer doesn't need to manually run a complex rollback script. They can simply type a comment on the incident issue, /rollback. A custom GitHub action sees that command, authenticates the user, and automatically triggers a workflow to redeploy the last known good version of the application. The fire is contained. This isn't science fiction. This is standard operating procedure at companies like Netflix and Shopify. Once the immediate crisis is over, the work isn't done. The focus shifts from recovery to resilience. The incident issue in GitHub becomes the foundation for the postmortem. It contains a perfect time-stamped record of the entire event. When the alert fired, who was involved, what was discussed, which actions were taken, and how the problem was resolved. There's no need to reconstruct a timeline from scattered chat logs and hazy memories. The team analyzes this record to understand the root cause. Not to place blame, but to understand what systemic weakness allowed the failure to happen. From this analysis, new work is born. Maybe they need better test coverage for a specific part of the code. Maybe a monitoring dashboard needs to be improved. Maybe the rollback process itself could be even faster. These action items aren't just talked about. They are created as new GitHub issues, directly linked from the original incident. They are prioritized, assigned, and fed right back into the development backlog. This is the feedback loop in its most powerful form. Production doesn't just inform development. It actively drives it. The system learns, adapts, and gets stronger with every failure. And this is where GitHub Copilot re-enters the picture, this time as a first responder. During a high-pressure incident, an engineer might be looking at a cryptic error message from a system they didn't write. They can paste that error into a comment and ask Copilot, explain this stack trace in the context of a Java Spring Boot application. Copilot will break it down, explaining the likely cause and suggesting avenues for investigation. Or imagine they need to query a massive data lake to find user sessions that were affected by the outage. Writing complex SQL or Custo queries under pressure is error-prone. With Copilot, they can just write a comment in plain English. Show me all users who experienced a 500 error on the /API/checkout endpoint between 10 p.m. and 10:15 p.m., universal time coordinated. Copilot translates that into the precise, syntactically correct query for their database or logging platform. It's like having a senior staff engineer from every team in the company whispering suggestions in your ear, instantly 24/7. It accelerates debugging and reduces the cognitive load on engineers when they are under the most stress. So let's zoom out and look at the entire picture we've painted. It's a perfect circle. A business need is captured as an issue in GitHub. A developer, aided by Copilot, opens a secure, cloud-based codespace and writes the solution. They submit a pull request, which is automatically scanned for security vulnerabilities by advanced security and validated by a suite of tests run by GitHub Actions. After a human review, it's merged and deployed to the cloud again by GitHub Actions. In production, the feature is monitored, and if something goes wrong, an alert creates a new issue in GitHub, starting the cycle all over again. This is the digital supply chain. It's the assembly line for the modern economy, and GitHub Enterprise is its operating system. It has fundamentally transformed what it means to build, ship, and operate software at scale. It has broken down the silos between development, security, and operations, creating a single unified platform where everyone can collaborate with complete context and transparency. The reason America's most innovative companies, from the fastest-growing startups to the Fortune 50 behemoths, have standardized on this platform isn't just because it's a good place to store code. It's because they understand that the speed and quality of their software development process is their primary competitive advantage. In a world where every company is becoming a software company, the one that can turn an idea into secure, reliable, customer-facing value the fastest wins. GitHub Enterprise isn't just a tool they use. It's the engine of their innovation. It's the framework that enables a culture of continuous improvement, of learning from failure, and of empowering developers to do their best work. It is the invisible yet indispensable foundation upon which the next generation of technology is being built, right now. It's not just how they manage code, it's how they manage the very pulse of their business.